Welcome back. We have been trying to establish a connection between topology and condensed matter systems, and in general we have done that for quantum mechanical systems such as electrons or the Aharonov-Bohm phase that is in the vicinity of a solenoid. It's an additional phase that an electron can pick up. We are now more into the connection to condensed matter physics, and let me start with a topic which is quite important for understanding the later parts of this, and it's been used heavily in the study of condensed matter, and it's called as the second quantization. We'll have to understand these the way the Hamiltonians are deformed, etc., and why we bring in the topic of topology. So first we have to learn how to write down the Hamiltonian, and these techniques of second quantization will aid us in doing so. So we'll start with second quantization. That's a formalism, and this is a very important formalism in the study of either you talk about condensed matter physics or quantum field theory. It's very similar notations are used. Quantization. Okay, all right. So we this would be also interesting because we would like to write down the Hamiltonian in the tight binding form. Most of those Hamiltonians that we write later on would be having a tight binding form, and then we'll see that how a system is topological, the parameter regimes in which it becomes topological, and the properties that come along with. Okay. So why is this formalism important in general? So we are talking about many particle systems. Okay. Which means it consists of many particles, and these are identical particles. Okay. This is the main assumption of quantum mechanics, that the particles that we deal with cannot be distinguished one from the other. Okay. So they all are absolutely identical, and this identical nature creates a problem, and in the following sense, that when you swap two particles, that is exchange two particles, the resulting wave function picks up a sign or may not pick up a sign depending on whether they are fermions or bosons respectively. Okay. So if you have more than two particles, that's three particles, so you have to keep a track of two such swaps or exchanges and three such or rather one swap is swapping say A and B, and the other swap is say swapping A and C or B and C, and so on. Okay. So let's just talk about two swaps. In a four particle system there will be three swaps and so on. Each time you make a swap and you're dealing with fermions, then you have to change the sign in the following sense. We'll just show that. So this becomes a big problem to deal with a large number of particles, and we often have to deal with large number of particles because the formalism of statistical field theory demands that we are actually talking about macroscopic number of particles, so that the statistical mechanics that we are familiar with can be applied. So in that context, we need to evolve a mechanism where such swaps between particles and the corresponding changes sign of the wave function can be incorporated. So let's just talk about one a particle to begin with. Let's say the state of the system is determined by these alpha 1. Okay. And if you are talking about n particles, so this for one particle, and say for n particles will have alpha 1, alpha 2, and then alpha 3 and so on, and say so we are dealing with n particles and alpha n. Okay. And this will form a state. okay, a complete set of states and so on. So, this will form the Hilbert space. Now, can we simply multiply it to write down the resultant ket, that is whether this one is a possibility. The inner product states and so on. Okay. So, this is incorrect because of the reason that this does not give rise to these permutation of particles or exchange of particles. So, we will see how. So, let us talk about just two particles to make matters simple. So, either for fermions or bosons, we can write down the resultant state as say psi is equal to, we do the normalization as well, and we can write it down as say alpha 1, alpha 2 and plus minus alpha 2 alpha 1. Okay. This can also be written as 1 by root 2 alpha 1 alpha 2 plus minus alpha 2 alpha 1, and where the plus sign refers to bosons and the minus sign refers to fermions. Okay. And 1 by root 2 is the normalization factor. Now, for two particles, we start with the single particle states, which are alpha 1 and alpha 2, and form the complete set of states for these system of two particles, which are coming as plus or minus of when they are, the order is reversed. So, alpha 1 alpha 2 and alpha 2 alpha 1 and so on and so forth. Okay. And you can do it for three particles. It is going to be complicated, and you will have probably 6 terms and so on, and you will have a 1 by 2 factorial here, there you will have a 1 by 3 factorial, which is 1 over 6 and so on and so forth. Okay. So, for n particle, it is quite difficult to write down the state psi, and because all these combinations that come because of these various swaps that you do, that is very difficult to keep a track and write down a sort of wave function in this particular fashion. So, what I said is that you can't simply write it down as alpha 1, alpha 2 etc. as a ket and pretend that that is a many particle wave function that you have to deal with. You have to deal with something much more complicated than that. Okay. And as I said that the plus sign, which means that the bosonic wave functions are symmetric under the exchange of particles, whereas the fermionic wave functions are antisymmetric, which means that they pick up a sign as you change these two particles, and you make one more change, then it returns back to the same state. What I mean is that if you have 3 particles and you take 1 to 2 and 2 to 3, then it does not pick up any sign, because there are 2 minus signs that are being picked up. Okay. So, this problem is actually arising because of the indistinguishability of the particles. So, this wave function that you see here, because of the indistinguishability, you have to take combinations, but that is indistinguishability also gives you, or rather it provides you a solution as well. Okay. And that solution is provided by going into a Fock space, and this is discovered by V. A. Fock, was a Russian mathematician. So, we will discuss very quickly what Fock space is, and if you need to understand what Fock space is, let us just talk about bosonic system just to begin with, so that because the fermionic system, the number of particles is 0 and 1. So, I already gave you the answer that will not really worry about that which state to put a particle in. So, we will just worry about how many particles are there in a state. So, we will go from these representation of putting a particle in a given state to count the number of particles corresponding to a given state, and this is called as a Fock space. Okay, so it's called as a occupation number basis and so on. Let us say that we have a quantum state. Suppose a quantum state is 1 1 1 2 2 2 3 3 4 5 6 and so on. Okay. Which means that there are these particles, there's 3 quantum states containing 1 particle, 3 quantum state containing 2 particles, and 2 quantum states containing 3 particles, 1 quantum state containing 4 particles, 1 5 and 1 6 and so on and so forth. Okay. This is like a sort of huge redundancy in its representation. It will be much better if we just number the states in the occupation number basis and write the state in terms of how many particles in a given state. So, we will just count the number of particles n1, n2, n3 and nn. So, these n particle, so there are these subject to, of course, these things that ni, so I equal to 1 to n has to be equal to n. Okay. So, this is the total number of particles. So, the Fock space has n1 particles in state 1, n2 particles in state 2 and so on. Just like there are 3 particles that are there, 3 quantum state correspond to 1 particle and so on. Okay. So, this is called as the Fock basis, and this will help us in writing down a second quantized Hamiltonian. Let us see how. Okay. So, Ni can be anything for bosons. Okay. So, this is an important point, and Ni is equal to 0 and 1 for fermions. Okay. So, either a given quantum state can have 0 particles, that is no particle, and or it can have at the most 1 particle. Okay. We are not talking about spin at this moment, but that can also be incorporated. This is basically provides you, of course, a simplification in writing an n particle state, and but then we still are not sure that how this representation is doing justice to this exchange of particles or the swap of the particles, and let us see how that is being done. So, that is done by using creation and annihilation operators. Okay. So, these are represented by the creation operators are represented by C dagger, it can be A dagger or B dagger depending on sort of notations that are used by various authors, and the annihilation, which is also called as a destruction operator, this is represented by C. Okay. And so, what does this do? This really does this. So, it is C I, it acts on these Fock space which contains n1, n2, ni and nn. So, this is nothing but equal to 1 minus ni and minus 1 whole to the power epsilon I. I just tell you what epsilon I is, and n1, n2, ni plus 1 and nn. Okay. So, what it does is that it increases the number of particles in the ith level by 1. Okay. So, this is what it does, and in the process it picks up this factor and this factor. We will just tell you in a moment what these factors are, and you have a Ci, that's this is for the creation and this is for the annihilation. So, Ci N1 N2 Ni Nn, this is equal to Ni into minus 1 whole to the power epsilon I N1 N2 Ni minus 1 Nn. Okay. So, what is epsilon I? Epsilon I is a quantity that considers this swap. So, it is a sum over all the nj's prior to that I. So, this j runs from 1 to I minus 1. So, you count all of them, their occupancies. We are particularly writing in terms of fermions, such that so these are for fermions. We are not talking about bosons, but they can also equivalently be done provided you do a symmetrization of the wave function. This is very specific to the nature of fermions and bosons. The fermions obey an antisymmetric property, whereas the bosons obey symmetric property. Wave function is symmetric under the exchange of particles. Okay. And this is one of the reasons that the fermionic wave functions are written as Slater determinants, because the properties of determinants are that if you exchange a row and or a column, that is, you exchange say third row with seventh row and so on, or you exchange a fifth column to 14th column for a given determinant, it picks up a sign, a negative sign. You do two such swaps, it picks up another negative sign, which means the net sign will be positive. And very importantly, if you make two of the rows or two of the columns identical, then the determinant is equal to 0, which is related to the exclusion principle, Pauli's exclusion principle, which says that no two particles will be allowed to occupy the same quantum state, okay, with all their quantum numbers to be identical. Okay, we are at this moment we are not talking about spins, but if they have different spins, then they can occupy. Okay. So, epsilon I, which is there in the exponent of this minus 1 whole to the power epsilon I, minus 1, so it is in the exponent of this minus 1, that takes care of these swapping of the particles. Okay. And these 1 minus Ni in this expression for the creation operator that you see, it ensures that if the particle already has an occupancy, that is if an electron is already sitting in this state, then no more addition can be done, or it is allowed. So, this is that 1 minus Ni, and this Ni that you see, I am sorry, I forgot to put an equality sign, and this Ni that you see is it makes sure that the occupancy can never be negative. Okay. So, it is either 0 or 1. Now, these things obey anti-commutation relation. And what are anti-commutation relations? They are just like commutation relation that you are familiar with. Just to remind you that xp commutator is equal to I h cross. That is a commutation relation, which means xp minus px is equal to I h cross. These are operators. Okay. So, you can, if you want, you write it with a cap there. So, all these applies to the operators and so on. So, these are not just not quantities that we are talking about, and similarly there are like all these commutation relations that we are familiar with for the angular momentum, which is IH cross L. So, this is like it encodes a number of commutation relation for the components of the angular momentum. Okay. So, all these quantities that are fermions, bosons and spin etc., they have their own commutation relations, fermions have this anti-commutation relation which I just said. The bosons obey commutation relations, and the spins have their own commutation relations. Okay, they do not match with the ones for the fermions and the bosons. So, what I mean is the following. So, this is how it is written. Now, there are different notations that you might find, but mostly it is done written with a curly bracket instead of a square bracket. But sometimes a square bracket is followed by a plus sign. This also means anti-commutation. Okay. Because there are opinion about notations that people follow. So, this is equal to Ci dagger Cj dagger plus Cj dagger Ci dagger, this is equal to 0, and similarly you have a Ci Cj anti-commutation. So, anti-commutation very importantly you see that this plus sign is the main thing. Let me write it with a color so that you are sensitized about this, the main thing about the anti-commutation relation. So, it is Ci Cj plus a Cj Ci, and again this is equal to 0, and a Ci dagger Cj. So, this is equal to a Ci dagger Cj plus a Cj Ci dagger, and this is not equal to 0, but this is equal to a delta function, a Kronecker delta with delta ij. What it means is that if I equal to j, then this is equal to 1, that is if you have Ci dagger Ci plus Ci dagger Ci, then of course this is equal to 1, and so on. Okay. And there are various properties that we can talk about, the number operator and so on, which you will see. Okay. So, these anti-commutations that you see are they ensure that there is a this plus sign actually or the anti-commutation relation ensures that there is a minus 1 whole to the power epsilon I, and that will take care of all the swaps that are affected in writing down the many particle wave function. So, we will write down the ket as n1 nn, this is equal to a C1 dagger and a Cn n dagger whole to the power n 1 n n, and multiplying by or rather operating, not multiplying, it is operating on a 0, and this is actually a many body vacuum. Which means that it does not have any particles, but that particles means in the many particle sector it is a vacuum. So, this is how it is written, and how these are so useful and why would this we have to learn this is the following. When we try to write down 1 and 2 body operators, which are all what are there in the Hamiltonians, you see sort of in general the scattering problems are all 1 body and 2 body problem. A 1 body problem is that expresses the kinetic energy of the particle, the body it's just 1 body, how it moves and so on. And when you talk about 2 body problem, then we talk about the interaction between 2 particles. Okay, 3 body onwards, it is almost unsolvable in most of the cases because of the phase space that you have for which are defined by the momentum and energy conservation laws. They are not enough to find out deal with a 3 body scattering process. Okay, there are some specialized techniques which one does, but anything more than that of course will be treated as a many body problem where you would talk about them statistically. Okay. So, what is this one body operator? So, one body and two body operators. Okay. So, let me write down a kinetic energy which is equal to sum of the all the kinetic energies. So, I equal to 1 to n, k is the kinetic energy, and this can be written as using the complete set of states. We can write this down as alpha alpha. So, this will give you, I will tell you that, and this is that k and beta beta and so on. Okay. So, alpha and beta are single particle states, and these alpha this is called as an outer product, and these a completeless relation would give this, and similarly for the betas they would give this as well. Okay. So, this is why the this I should write it with a I and so on. Okay. So, these are the so this is an I and so on. Okay. So, I just introduced this complete set of states, and then we can write this down as alpha and beta and I and so on, and then we can write this as alpha and then k I and then beta, and then we can sort of take a alpha and beta and so on. Okay. So, that we use this and it is also alpha equal to 1 and beta equal to 1. So, we left multiply by a vector which is alpha. So, it is a ket of alpha. So, that this becomes equal to 1, and we use a beta here which becomes equal to 1, and that is because we can multiply a 1 here. And so, these are written in terms of the matrix elements. So, these are alpha beta and I, and this is like alpha k I beta and C alpha dagger 0. So, alpha is written in terms of C alpha and a vacuum, and the beta is written as a 0 and a C beta. And this will also become equal to 1 because 0 is as much of an element of that Hilbert space as any other. So, this is finally what you get is alpha beta I is like a alpha k I beta and a C alpha dagger C beta, and this is a form of the one body operator. Okay. So, this is a number which is the expectation value of these k I. Say for example, in a continuum sense, this is like minus h cross square by 2m d2 dx2, and then you write down alpha and beta, and then this is the operator that comes out. So, it is a C alpha dagger C beta. So, if alpha and beta are, say for example, states that are they denote say position or something, okay, then this will be like a C I dagger C j and so on and so forth. Okay. And similarly, we can also write down this. I will not go in, but you can see this. We can write this down as for the potential energy. So, this V is equal to alpha beta alpha prime beta prime. So, this will be like a alpha beta and a V alpha prime beta prime, and this will be like C alpha dagger C beta dagger C beta prime C alpha prime and so on. Okay. So, this is nothing but the matrix elements of this operator, which can be for a Coulomb term. This is like minus E square over R, and so this is like a alpha beta alpha prime beta prime. So, the matrix element is this and the operator is here. Okay. So, the matrix element is given by this V alpha beta alpha prime beta prime and so on. Okay. So, this is quite helpful, and it will help us to write down these tight binding Hamiltonians that will be extensively discussing throughout this course. Okay. then it will be made clear, or rather it will be more clear, that why we have introduced these notations. And as I said, that they take care of this humongously large number of swaps, or the exchanges of the particles, or these signs arising from these exchanges, and they are taken care of very sort of in a very smart way. So first we write down the Fox states, and then we introduce the these C and C dagger operators and their anti-commutation relations. We are talking about fermions, but similar way one can talk about bosons as well. The formalism leaves is exactly the same, excepting that we would be talking about commutation relations instead of anti-commutation relations. All right. So these are Hamiltonians. Now we are slowly, moving towards condensed matter physics, which deals with Hamiltonians for a given system, its energy levels, and so on. And these energy levels are called as the, the band structure, E as a function of k. Usually we plot it as a function of k. So this Hamiltonian, and let's talk about the Hamiltonian and relationship with topology. Okay. So I just a freehand drawing of bands, and say one band is like this, another band is say like this. This is the conduction band, and this is a valence band, and so on. Okay. So this is E versus K for a given system. I'm just arbitrarily drawing some two bands, and it can actually have many bands, but something that is too far away from the Fermi level is not interesting at all, because it doesn't contribute to the physical properties of the system. The ones that are closest to the Fermi level are only important for us to consider. And I mean, what is meant by near the Fermi level? So this is the Fermi level. So this is called as a Fermi level, and this is usually the zero of energy. So this line, let me then draw it with another color. Okay. So this is the Fermi level, and something that's far away from the Fermi level are not interesting. The ones that are close to the Fermi level, maybe within electron volt or so, are important. By the way, this 1 electron volt, even if it sounds a very small energy, especially the students who are familiar with high energy physics and so on, for condensed matter people, this 1 electron volt is a very large energy. In fact, this is roughly the energy that the typical semiconductors like germanium or silicon they have, or is aluminum, gallium arsenide, etc., maybe having 1 point something electron volt. 1 electron volt is 11,600 Kelvin. Okay. You understand the enormity of these energy. What I mean is that 1 electron volt, when you write it or equate it to kT, K is the Boltzmann constant, and put the value of the Boltzmann constant, and do all these homogenizing the units, etc., and then T comes out to be close to 12,000 Kelvin. It's 11,600, and that's a very large temperature, because the outside of sun is about 6,000 Kelvin or a little more than that. So anything in the world would melt at 12,000 Kelvin. Okay. So even though looks like the 1 electron volt is a small energy, you cannot really think of such a large energy in condensed matter systems. Okay. All right. So what I'm trying to get at is that suppose this Hamiltonian is a function of some lambda. We have used this notation earlier, where lambda is some parameter of the system, and then lambda can be tuned. Say for example, lambda can be the electric field or the gate voltage for a system for which you are writing down the Hamiltonian, and then you are slowly tuning the gate voltage, and the Hamiltonian changes. And say the Hamiltonian changes in this manner that as a function of lambda, it's sort of, there are only two levels that I wrote down, and then it sort of these two energy levels in the both in the conduction and the valence band, they get slightly, they change slightly as it's shown here, but they do not cross the Fermi energy. Again, the Fermi energy is at the middle. Okay. So, now I am not plotting it as a function of k. I say I am at a given k, and then I am plotting it as a function of lambda. Okay. Do not mind, this is just an example that I am giving. The plots look same versus k. K is the wave vector, by the way. So, let me write that. K is the wave vector and lambda is some parameter. Okay. Some parameters such as gate voltage, or say spin orbit coupling, and which can be tuned by using some external means, etc. So, it can be anything, and I am just showing that that a situation in which it is changing with lambda. But let me show another situation where again I will show the Fermi energy with red, and so it happens like this and so on. Okay. Again as a function of lambda. So, this is E versus lambda and so on. Now, see, there is a big difference between this picture, let us call this as 1 and let us call this as 2. Okay. In 1 and 2, the difference is that the number of levels, the number of energy levels, or the number of bands, energy levels below the Fermi energy changes in 2 remains same in 1. Okay. So, 1 means this one, and when I say 2, what I mean is that's Roman 2, the figure I am referring to. Okay. Now, let me sort of changes in 2 and remains same in 1 we underline, and this will decide that whether the system is topologically equivalent as lambda is being is tuned, this parameter lambda is tuned. In case 1, the system is in the same topological state, then topological invariants are same. What I mean to say is that if you refer to the lecture in the last one that we have delivered, there the mug changing into donut. So, this will be so mug changing into donut, the systems are topologically equivalent. We said a number of times that a smooth deformation of the system from the mug to the donut leaves the system topologically same. That is their identical, because there is just one hole, it just counts the number of genus present in the system. So, where you hold the cup is the hole that it transforms into the donut, and that is only thing that happens. Okay. The system remains topologically same. Okay. So, these are the two inferences that comes out. Okay. These two inferences emerge from this particular plot. This is just a just a schematic plot. Do not worry too much about this. I have just shown two energy levels, 2 below the Fermi energy, 2 above the Fermi energy, and so on. However, here these systems are topologically distinct. okay, because the Hamiltonian, for which energy is the eigenvalue of the Hamiltonian, it does not remain invariant, rather the number of levels below the Fermi energy as a function of lambda. Till this point there are two levels above and two levels below, but this point onwards, whatever that point is, let us call that as lambda c, that point onwards there are three levels below, and which is not the same as two levels. So, the system undergoes a topological phase transition, which means that there is a gap closing scenario that occurs, which means that you are puncturing or you are tearing something in order to create a different, either a differently topological system, that it has different topological invariant, that is you are making a mug into by somehow piercing it or breaking it or drilling some hole into it, you are creating another genus, that is it sort of is equivalent to now a spectacles, the pair of spectacles that people wear. So, they are topologically distinct, and this topological distinction is accompanied by a gap closing scenario. So, these are the two important features of these two things that, or these two plots that I have drawn. Okay. So, I hope that if you read more, of course, you will agree with me more, but I hope I have been able to give you this analogy between topology and condensed matter physics, that this is how you slowly deform a system, and if the system remains invariant, that is a sort of becoming a donut, then they are topologically equivalent, which is farther corroborated or supported by this Gauss-Bonnet theorem, whereas this system you have to make some drastic changes to the system, and in language of condensed matter physics, it means that there is a gap closing occurs. You see the gap, it was earlier gapped, it was here gapped, but that gap closes with the Fermi energy at this point lambda c. This point is lambda c. This is what I mean as lambda c, and this gap closing occurs and so on. Okay. So, then the system does not remain topologically equivalent, that is a mug donut sort of in that sense the equality or the similarity does not remain, and one actually gets a different system. Okay. So, one the Hamiltonian representing the two systems before lambda c and after lambda c are not topologically equivalent. Okay. The topological invariant changes. Okay. So, now this topology etc. and its relation to condensed matter physics can be understood even better by looking at the symmetries of the Hamiltonian. So, let us see what we mean by symmetries of the Hamiltonian. So, every day we come across a lot of symmetric objects, say for example, a circle is a very symmetric object. If you sort of turn it, make a rotation by some angle theta, you will be not be able to distinguish whether it is an earlier circle or a new circle which is rotated by theta, or say a sphere, or there are many symmetric objects. There are like many things in nature which are symmetric. Suppose these leaves that you see which have got a symmetry. There are these alphabets, many of the alphabets have got symmetries along various lines, like for example O has a symmetry about any of the axis, or M has a symmetry about the vertical axis, and so on. Okay. So, these Hamiltonians also have certain symmetries, and these symmetries dictate whether as a function of lambda, whether the system will undergo a topological phase transition or will remain equivalent to the original system as you change lambda. Okay. So, these symmetries are really distinct from the crystal symmetries. These crystal symmetries come in say all these group theory that you might have studied, in which people talk about symmetries such as C4V symmetry, C6 symmetry, and so on and so forth. So these are distinct than that. And there are a few symmetries which are really important, and we'll study them. And one of them is called as a time reversal symmetry. In short, we'll call a TRS. Then we'll talk about symmetry, which is it's called inversion symmetry, or it is also called as a parity. Okay. So there's, if you invert the coordinates, or you know, so how does the system or the Hamiltonian behaves with the inversion of this, that is r going to minus r, how does the Hamiltonian behave? So that's called inversion, or it's also called parity. Then there are these symmetry called as the, you know, the particle hole symmetry. It's called PHS. It's short name for that, and this is particularly important in the context of superconductors. And then we have chiral symmetry and so on. Okay. Now this particle hole symmetry is also called as a charge conjugation symmetry. Okay. And so on. So let us you know, start with the time reversal symmetry. And you might wonder that what is reversing time? I mean, is there anything called time goes in the other way? That's not true. What we still do is that we want to understand whether the system moving on the towards the right with a velocity v, whether that scenario remains unchanged as the particle moves in the other direction with minus v. Okay. So if the direction of motion of a certain particle which is expressing you know, being expressed by the Hamiltonian, if that changes, or that changes sign, then what happens to the Hamiltonian? Does the Hamiltonian remain same, and so on? And we'll see that this has very significant you know, effects on the condensed matter physics, because there's something called Kramer's degeneracy that will emerge. Just talk about it. You know. So let's talk about time reversal symmetry. Okay, so I will not go into details how the form of the symmetry operator comes, but I'll just tell that this is the symmetry operator and try to, you know, justify the behavior of the Hamiltonian on that. Okay. So under time reversal operator, it's usually written with a curly t, but it's easier for me to write this straight t. Under this, it is written as t going to minus t. Okay. So under time reversal, we are talking about a system without spin. So one system without spin degree of freedom. And you might wonder that if you are talking about electronic systems, or even bosonic systems, they have spins. Okay, so how can you ignore spins? And we can ignore spins in a variety of cases. Suppose the system is spin polarized, which means that it has only spins pointing in the, say, talking about a spin half, pointing in the positive z direction, in which case you have only that kind of systems, and or they are pointing in the opposite direction. Okay. So, now the system does not distinguish between the particles pointing in the opposite, the spins pointing in the positive z direction or negative z direction. If it does not do that, there is no term that mixes the spin, one kind of spin to another, then you can just talk about one kind of spin and then extend that analysis to the other kind of spin as well. And then the spin really does not arise into the discussion that we carry on later on. And you just put a, if you need to sum over both the spins, you do a factor of, put a factor of 2, but otherwise the spin does not enter into the discussion. So, so under TRS, this T, T small t goes to minus T, and the Hamiltonian commutes with the time reversal operator. Okay. So, time reversal operator simply changes T to minus T, and the Hamiltonian commutes with that. Now, if you want to know that my Hamiltonian may not only contain T, it contains X and P and so on and so forth. I will show you all these properties. So, A, if it is T X T inverse, this is how it is, the operation is talked about or discussed. It is T X T inverse is equal to X, then you have T P T inverse is equal to minus P. So, the X, that is the position variable, does not change sign, but P, which is equal to V over T or dV dt or dP dt, I mean this is like it involves P is equal to mV. So, it has a V, V has a X by T, since T changes sign, so P has to change sign. So, so this is another one, and the important thing is that if it gets a I anywhere, which is I equal to root over minus 1, then it changes it over to minus I. Okay. So, and if you like, T L T inverse, that is L is the angular momentum, that also picks up a negative sign. Okay. So, if you want a little more on that, it is not required, but then X and P is I H cross, we know. So, this is equal to T I H cross T inverse, and by the third property or C property, T I T inverse will become equal to minus 1. So, this becomes equal to minus I H cross, which is equal to a minus X P commutator. Okay. So, X P commutator does not remain invariant. So, let us go to this F. So, that tells you that if you have a real space second quantized operator T C J, for example, T inverse. So, this remains same. However, T C J dagger T inverse, that also of course remains same. But if you write it in the K space, that is a wave vector space, so T C K T inverse, this is equal to C of minus K. Okay. And similarly for the K. So, this is F, G, H and so on. So, I am talking about this C in the K space. We have not specified earlier what alpha and beta are. They could be valid momentum states written in the momentum eigenbasis or in the position eigenbasis. So, this is what it does. So, in this thing, what turns out is that the form of T is equal to the complex conjugation. Okay. So, K is complex conjugation. And T square, that is square of that, is equal to 1, or you can write it as a matrix 1 because T is usually an operator. So, T square gives you 1, that is if you do twice. So, T acting on I will give you a minus I, which is in C, and then when I do it on this other side, that is T acting on minus I, T inverse, that gives you I. So, T square becomes equal to 1, so this is like if I right multiply by t or left multiplied by t, then that t square becomes equal to 1. So, this is where k is the complex conjugation. This is slightly different when system with explicit spin degrees of freedom is there. Okay. Okay, and we are talking about spin half. Okay. So, again I mean H and T should commute if a system has, this means that TRS is a valid symmetry operation. That means the system has time reversal symmetry. Okay. So, it is written as the operator is now no longer just k or the complex conjugation, and we also have t acting on the wave function will give me say psi t, and the psi t and psi are distinct, and so psi and psi t this is equal to 0, both psi has eigenvalues, that is E as the eigenvalue, and psi t also has E as the eigenvalue. What it means is that H acting on psi will give you E psi, and H acting on psi t gives you E psi t. I am telling you all the results a priori, and this is nothing but what is called as a Kramer's degeneracy. This along with this condition. Okay. So, for a given system, if the system has time reversal symmetry, in that case the wave function psi corresponds to an energy E. There is also the time reversed state, which is psi t here, where you apply psi on the I mean the time reversal operator on the psi and becomes a psi t, then the inner product of psi and psi t is 0, that says that these are orthogonal states psi and psi t, and each of them have energy E, that is H acting on psi will give you E psi, and H acting on psi t will also give you E psi t. Okay. So, the time reversal operator in this particular case has a form which is exponential I sy. This sy is we are talking about spin half. I told you that. So, this is has to be it is a spin half operator, y component of the spin half operator, and this k, which is a complex conjugation. And if you write down S is equal to H cross by 2 sigma, in order to convert that into Pauli matrices, then this becomes equal to e to the power minus I pi by 2 H cross by 2. Yeah, sorry, I forgot this H cross. So, it is H cross and then a sigma y and a k. Okay. So, this is the form of the operator for a system with spin degrees of freedom. So, if you take a t square, now what is this exponential minus I pi by 2 H cross sigma y? How to calculate this? If you remember that it is a exponential I theta sigma dot n. This is how the exponentiation of the Pauli matrices are done. Sigma is the Pauli matrix which has components sigma x, sigma y and sigma z, and n cap is just a direction. This is equal to, by using this de Moivre's theorem and properties of these Pauli matrices, it is equal to this, and I sigma dot n cap sine theta. Now, here you see theta is equal to pi by 2 and n cap is equal to y cap. Okay. So, the first term goes to 0 and the second term gives you, so this is a minus. So, there is a minus, there is a plus minus, there is a plus minus. So, exponential minus I pi by 2 h cross sigma y, you can take h cross equal to 1 if you like. So, this is equal to, let me take h cross equal to 1, that will be better, and this is equal to I sigma y, and that is all. I mean, at theta equal to pi by 2, the first term is 0 and the second term gives you sin theta by 2 equal to 1. So, it is simply I sigma y. So, t is equal to I sigma y k. Okay. So, if you want to calculate t square, so this is equal to I sigma y k into I sigma y k. This is equal to I square and then sigma y square, which is equal to 1, and then k. So, this becomes equal to a minus, I mean this becomes equal to a minus sigma y square, and this is equal to a minus 1. Okay. So, that tells you that the system with without spin degrees of freedom t square is equal to 1, and with spin degrees of freedom t square is equal to minus 1. So, the square of the time reversal operator changes as you talk about spinor particles, that is spin half particles or spinless particles. Okay. So, once again I will show you the Cj up dagger T inverse, and this is equal to minus Cj down, and T Cj down T inverse, this is equal to Cj up. So, it tells you that if you have a j spin, I mean a particle with at a site j with spin up, it makes it the spin becomes lowered, it is rendered lower, and there is a minus sign, and for the lower it becomes up and with no sign there. So, now T h of k, suppose you have a tight binding Hamiltonian where the Hamiltonian is written in the k space, this is equal to, so T inverse is equal to h of minus k. Okay. All right. So, this is about the time reversal symmetry, and on the next lecture I will be talking about the inversion symmetry and particle hole symmetry and the chiral symmetry and so on. Okay. So, what we have given so far is the first two classes, they were concerned with establishing what topology is, and the various properties etc., or through various visual or graphic and demonstration, we have said that a system remains invariant if it has the same number of genus as you deform the system. Now, what is its relation to condensed matter physics, that needs to be understood, and when we say that these deformation is nothing but driving the system which is a function of certain parameter, and then whether the entire property of the system changes, that is the number of energy levels below the Fermi energy, does that get altered? If it does not, then the system remains it is as a function of lambda, it goes into or rather it remains topologically identical, so a mug becomes a donut. But however, if the number of energy levels are altered, then you have done something violent to the system, and there the system undergoes a topological phase transition from so it will be a different topological invariant including a 0. Okay. So, which means that system goes from topological to trivial, that is non-topological when the this genus or this thing is topological invariant is 0. We will continue with this symmetry for just a while, and then we will go on to materials which shows these topological properties. These are called topological insulators. Most of the course will be talking about topological insulators. Thank you for your attention.